Hello physicists, today is our last day where we're going to be presenting new stuff from Unit 2. So a lot of today is going to be review, and then we'll introduce one new idea, the idea of a circuit where we include both a resistor and a capacitor, so poetically called a RC circuit. And so also we're going to be discussing some stuff that might be relevant for the quiz and for the test next week. And we're going to be talking about the functions of voltmeters, ammeters, and ohmmeters, which you've used in labs this week. So, first things first. We've been talking about capacitors for quite a while. Remember, capacitors hold charge. The parallel plate capacitor's capacitance, which tells you how much charge is held for a given voltage difference. Remember, it's a plus charge on one plate, minus charge on the other plate. Total charge is 0. We've also talked a lot about equivalent capacitance and realized that if you put a bunch of capacitors in series, they can act like a bigger capacitor. If you put a bunch of capacitors in parallel, they can act like a bigger capacitor. If you put a bunch of capacitors in series, they can act like a smaller capacitor. We've also talked about how capacitors store energy, and the amount of energy that they store depends on the capacitance of the capacitor and the voltage across it. So the potential difference across it. And why is that storing energy? Well, it's because equivalently, it would take work to put these charges on the different sides of the plates. So you can imagine taking those minus charges and bringing them over here, so that would take energy. Equivalently, you could also think about that energy as being stored in the electric field between the plates. Now this week we've also talked a little bit about electrical current. Now, this is different from our case with a capacitor, because in the case of the capacitor, after a while, the charge is just sitting there. And the energy from that charge didn't leave the battery. It left the battery, but it didn't leave the circuit. That energy is still being stored in the capacitor. On the other hand, with resistors, the energy is leaving the circuit. So we're having charges that are being accelerated by the battery, but then they lose that energy that they've gained once they go through the resistor, and it becomes heat. Now you might remember that the electric field is dependent on the change in voltage over the change in distance, right? We could write that as a derivative if we wanted to. This is just like the electric field in the x direction, but the interesting thing here is that we've now moved on to talking about Ohm's law, which we're talking about currents in terms of voltages and resistances. But we could be thinking about current densities in terms of electric field if we wanted to think about how long is this. You could think about how big the potential difference is and convert back to talking about electric fields if we wanted to also talk about current densities instead of currents. Regardless, we have been talking a lot about just currents and voltages in the last week, even though we realize that resistance rolls a lot of different things together. It rolls the resistivity of the material and the geometric factors like the length of your resistor and the cross-sectional area of your resistor. And then those all are factors in determining how much power is used by the current going through that resistor. So the bigger the voltage and the bigger the current, the bigger the power that's radiated out. Okay, so you're losing energy, you're spending energy in your circuit when you have a resistor. All right, so here's a nice question. It says the insulated wiring in a house can safely carry a maximum of 18 amps. The electrical outlets in the house provide an alternating voltage of 120 volts. A space heater, when plugged into the outlet, operates at an average power of 1500 watts. Okay, so P equals 1500 watts. it tells us that the current it then asks how many space heaters can safely be plugged into a single electrical outlet and turned on for an extended period of time. So if our P is 1500 watts and our V is 120 volts, let me grab my calculator quick. Okay, I've grabbed my calculator. We take 1500 divided by 120, and we get a P equals IV. So here the I must be 12.5 amps. It says the insulated wiring in a house can safely carry a maximum voltage of 18 amps. So if we've got 12.5 amps already tied up in one of our space heaters, if we had two of them, it would take 25 amps, and that would be more than we could handle. So we're going to be able to just have one space heater on at a time per outlet here. Okay, so here's another question. I've made it, hopefully I've mentioned that V equals IR is not really a law of nature. It's a rule that more or less applies to certain types of objects over a certain range. So take a look at this question. It says a certain circuit contains a battery and a resistor. An instrument to measure the current in the circuit, an ammeter, is connected in between one of the terminals of the battery and one end of the resistor. The graph shows the current in the circuit as the voltage is increased. Which one of the statements best describes the resistor in this circuit? Okay, so then it says the resistor does not obey Ohm's law. The resistor obeys Ohm's law for some voltages, some voltages, some voltages. So let's take a look at this. This graph. V equals IR says that as we increase the voltage, the relationship with the current is going to be linear, and that R is the slope here. So in this case, let's look. It looks to me like this thing is approximately linear. It's just going up and up and up and up until about 25 volts. And there we have a kink at 30 volts. There's another kink at 35 volts. There's another kink. So past 25 volts, this object shows non-ohmic behavior. But the resistor does obey Ohm's law between 0 and 25 volts. And that's pretty normal. That's what we expect. We expect that objects that we call resistors are only going to be resistors over a certain range. And so if we're going to be engineers and go and design devices, we have to know what that range is. We're going to have to test it to be certain that we're not making expectations that our objects cannot fulfill. Now, in that last question, you'll notice that it was talking about putting in a current measurement and putting in a voltage measurement. So in lab this week, you used voltmeters, you used ammeters, and hopefully now you have a little bit better grasp on what the difference is. Voltmeters measure voltage in parallel. So if you want to measure the voltage across a resistor, for instance, you can simply take the wires from your voltmeter and put one wire on one side of the resistor, put the other wire on the other side of the resistor. On the other hand, if you want to measure the current, you actually have to put the ammeter in as a part of the circuit and run the current through the ammeter. Now, both of these are passive devices. They're just leeching off a little bit of the voltage from this circuit. So you're not going to break the stuff in the circuit, but you might break, for instance, your ammeter if you put it in wrong. The reason is that this voltmeter has a really big resistance. And so essentially, when you put it in parallel, it is going to experience the same voltage that's across here because it's connected by a wire, but because it has a really big resistance, it doesn't pull much current. So it's supposed to not change what's going on in the circuit very much. Conversely, the ammeter has a really small resistance. So when you put it in series with the resistor that you already have in the circuit, it is supposed to not change the resistance very much. So this resistance has to be much smaller than the resistance of the thing that is the primary circuit element. Okay, so ammeter has to have a really small R. Ohmmeter or a voltmeter has to have a really big R. And because the ammeter has such a small resistance, it's very possible to break an ammeter. If you put it across here and just put a big voltage, you want the voltage across this thing to be very small. So that's why we're putting it in series. It's acting essentially as just another wire in our circuit, and it's very easy to burn out the fuses in ammeters, as we have seen in lab this week. Now, the thing to be a little aware of is that an ohmmeter actually acts quite differently. An ohmmeter is supplying a voltage, it's supplying a set voltage, measuring the current that results, and then estimating what the resistance is based on V equals IR. Okay, so this is sort of the independent variable. This is the dependent. That's what they measure. And then this is inferred. Okay, so when you use an ohmmeter, you're trying to measure the resistance in ohms, but really what you're doing is not so different from what you did when you had an ammeter, except that the only difference is that the voltage is inside the multimeter now. It's the battery of the multimeter is providing that voltage. So that's why we had to take the circuit element out of our circuit before we measured the resistance. Okay. Now, last class period, the hard thing. I don't want to build it up too much, but these can be tricky. The hard thing that we introduced were Kirchhoffs Laws. And the thing that I was trying to stress last video is that Kirchhoffs Laws basically are just restatements of charge conservation and energy conservation. So the junction rule is just saying that all of the charge that comes in has to equal the charge that goes out of a junction if we're have a circuit that's in its steady state. Okay, so it's like thinking about water through pipes. If the water comes in, it has to go out. So the amount of current going in has to equal the amount of current going out. The loop rule reflects energy conservation. So essentially, it's a little bit hard to think about because the current is made of many particles that are going every which way. But on average, the average energy that you're going to gain by going across the battery has to be equivalent to the sum of the energies that you're going to lose going across the resistors. And when you translate that into the language of potential differences, it just means that the E applied here minus your voltage across V1 minus V2 minus V3 equals 0. And of course, the way that the reason this was useful is that we put this in terms of our current using V equals IR. Okay, so by using Kirchhoffs laws and Ohm's law, we can do quite a bit. So let's look. Here's quite a simpler problem than the one that we considered last time, and it's one that we'll be able to solve. I believe I put this one on your homework. So let's just do it together because I know that people are going to have problems with it. So let's look at it. You've got three batteries. You have a 6-volt battery, a 12-volt battery, and another 6-volt battery. And to start out, let's guess what directions our current is going. So it says, using Kirchhoffs Laws, write down the system of 3 equations that allows one to solve for the current flowing through each of the 3 batteries. What is the current through the 4 ohm resistor? Okay, so let's, first step, we're just going to guess what direction the current is flowing. Okay, so let's guess it's going through our batteries in the right direction. It might be right, it might be wrong. If it's wrong, we'll just get a negative current and we'll realize it was going the other way. So there's our I1. Here's our I2. And there's our I3. Okay, and then to be self-consistent, this current has to be the same as that current. So it's just going around the loop like this. So there's our I1. This current has to be the same as that current because there's no junction. So this one has to be the same as I3. And now let's go ahead and write out our Kirchhoffs laws. So the first Kirchhoffs law has to do with the junction rule. In the junction rule, the current going in has to equal the sum of the current going out. So in this one, we have I2 is our current going in, and then our current going out is I1 and I3. So that's our junction rule. And our loop rule, well, we have 3 different possible loops. This is a nice loop, this is a nice loop, and we could also do the outer loop right there. So let's just try the inner loops first and see what those look like, see if they help us. The rule is that if we sum up all of the voltages, it will be 0. So here we're going with the direction of the current through a, so our loop is going to go like this. Okay, and we're going with the direction of the current through a battery, so that's going to be 6 volts. We're going with the direction of the current through another battery, so that would be plus 12 volts. Now we're going with the direction of the current through a resistor, so that's going to be minus, we're expecting to have a voltage drop there, so it would be minus I1 times 4 ohms. Okay, then our other loop would just be going around here. So that would be 0 equals, so let's again just start here. This would be 6 volts. We're going with the direction of the current, so it's going to be positive. Again, we're going with the direction of the current by going clockwise here. So it would be plus 12 volts. And then we're going with the direction of the current through a resistor, so that's going to be a minus. So that would be minus I3 times 2 ohms. Now this is a circuit that I've set up to sort of be easy to solve, because you could go ahead and add these two together and solve for I1 without doing any extra work. So right here, I've asked you to go ahead and solve for I1, and you could get I1 times 4 ohms equals 18 volts, which you could then solve for I1 equals 4.5 amps. Okay, so part A, we wrote down our 3 independent, linearly independent Kirchhoff rules, and then part B, we wrote down our current. So then we're all done. Now, it is interesting to notice that we do have an extra loop that we could go through. We could go around like this, and it would also be fine. So what would that extra loop be? It would be, we have to choose a direction on this one, because we're going to be going partly with the current and partly against the current. So here this would be 6 volts. And then I would be coming around my loop, but my loop would be going opposite the direction of the current through that battery. So that would be minus 6 volts. And then I would be coming through here, I would be going opposite the direction of the current through a resistor. So this would, instead of being subtracted, I would add that voltage. So this would be plus I3 times 2 ohms. And then here, for my last part, I would be going through the resistor in the direction of the current. So that would be minus I1 times 4 ohms equals 0. So that one is also correct, and you can quickly check that by noticing, okay, this equation is I3 times 2 ohms equals 6 plus 12 is 18 volts. So your I3 is equal to 9 amps. And if I go ahead and just plug these in, 6 volts minus 6 volts plus I3 is 9 amps times 2 ohms minus I is 4.5 amps, 4.5 amps times 4 ohms. Let's see, 6 minus 6, that's 0. 18 minus 18, also 0. So it checks out. Okay, so Kirchhoffs laws, everything works out. It can be a little tedious to solve if you have a more complicated situation. Now take a look at the circuit that I showed you on the last video. And I got us to the point where I said, all right, we have 3 equations, 3 unknowns. I've solved it. But then some of you were saying, oh my God, it doesn't look like you solved it. It looks horrible. And I hemmed and hawed a little bit, and I said, am I going to solve this on our next video? And I have decided no. If I give you a problem like this on the test, this is what it will look like. It will just look like you writing out or being able to identify Kirchhoffs laws. So right here, the question is, which one of the following equations is not correct relative to the other 4 that's a typo. This should be 3 equations determined by applying Kirchhoff's rules to the circuit shown. So let's look. Is this a rule? I1 plus I3 equals I2. So here's I1. So this also has to be I1. Here's I3. So this is all the same. There's no branching. This must also be I3. So I2, that's the current going into this junction, equals I1 plus I3. Okay. Now let's look. We've got some loops. 6 volts minus 8 volts I1. Okay, so we're going here. Let's look. We're going on this loop. It must be going along this direction. Minus 5 ohms times I2. Oh, okay, we're going around the loop here. So far, so good. Minus 4 ohms times I1. Okay, so far, so good. Equals 0. I like it. Now let's look, what is our next one? 6 volts minus 6 ohms I3. So 6 ohms times I3. Oh, that must be this one. Okay, we're going around this circuit now. 6 volts, 6 ohms times I3. Good. Minus 5 ohms times I2. Okay, so we must be on this branch. So far, so good. Minus 2 ohms times I3. Okay, seems all right. Equals 0. I like it. Okay, let's check our last one. 6 volts minus 8 volts I1. Okay, so we're going here. Minus 6 ohms times I3. Okay. Oh, wait a moment. Wait a moment. When I went through opposite the direction of my current through a resistor, that should be plus 6 volts I3. I don't like that one. Okay, so that one's not good. So essentially, you can follow around the rest of the way. This is wrong. I'm going backwards through the battery because my loop is oriented. I'm going around in a particular direction. So this should be minus 6 volts. Here I'm going I'm going backwards, opposite the direction of the current through my 2 ohm resistor here. So this should be plus, and then this is okay again. So I have a sign error, sign error, sign error. So this last one is not correct. So this to me looks like an okay test question. The other ones seem a little tricky. So if I give you a test question on Kirchhoffs laws, it's going to be sort of streamlined such that it won't take you the whole hour to solve it. It will be sort of a straightforward one that you can solve quickly. Now let's go to our very last topic of this unit, and that's an RC circuit. Now this is a little bit special because so far we've only done circuits containing just capacitors and just resistors. So how is that going to change if we put a capacitor and a resistor in a circuit? Well, let's think about it. We start out with a capacitor doesn't have any charge. Then you flip a switch. What happens? Well, your current will start flowing through here, and it will start going through this resistor, and how big the current is going to be depends on how big your resistance is. So if you have a really big resistance, it's going to be a small current. If you have a really big little resistance, it's going to be a big current to start out. But as that current flows in here, you're going to start getting some charging on that capacitor plate. And in fact, once the charging on that capacitor plate is such that the voltage drop is equal to the voltage drop of the battery, the current will stop flowing through the resistor. Okay, so it's a time-dependent process. The time it takes to charge depends on 2 things. It depends on how big is the resistor, and it depends on how much charge can the capacitor hold. So that's dependent on C. So this rate is dependent on both R and C. So we have a time constant. It turns out that ohms times farads gives you seconds. So if you take the resistance in ohms multiplied by the capacitance in farads, that gives you something that's in seconds, and it determines something about how long this circuit will take to charge up the capacitor. Now, interestingly, if we then disconnect this and we connect that, we can also discharge the circuit, and then our current would go like this. Our voltage, or our circuit would again take some time for that charge to drain completely from the plus side to the minus side, and it would depend on how much charge was our battery holding, and it would depend on how big is this resistance, because the bigger the resistance is, the longer it will take that charge to flow through. So again, that process will depend on R times C. So in both cases. So we would like to be able to quantify this. How exactly should we expect the current to flow through this? And to do this, we're going to write down some Kirchhoff loop rules. So take a look. The moment we connect these, all right, we are going to have a voltage rise, a voltage drop, and a voltage drop. And if we add together all of these, it's going to give us our Kirchhoff loop rule. So in this particular case, we're going to have, for our resistor, it's going to follow V equals IR. For our capacitor, the voltage is going to follow Q equals C times V, or V equals Q over C. Okay, so what would our Kirchhoff loop rule be? It would just be that 0 equals how big is the voltage here across the battery minus what's the voltage across the resistor? It's going to be I times R. And then what's the voltage across the capacitor? It would be Q times C. Or sorry, Q over C. So this is our charging rule. Now, let's think a moment. If we have a current, it actually depends on the amount of charge that's going through the resistor per unit time. So our I is actually dq dt. It's how much charge we get per unit time. So we can write this equation as 0 equals epsilon minus R times I, which is going to be dq dt, minus 1 over C times Q. Now look at here. I have an equation that just depends on Q. Epsilon is a constant, or it's a number that I can measure from my battery. R is a value I could measure with an ohmmeter. C is also a value that I could get. So I can figure out what the current is going to do in this circuit if it starts out uncharged. Now I could also do the same thing with a discharging circuit. So this is my charging circuit. There's my discharging circuit. In that case, the voltage source is going to be your capacitor itself. So your loop in your discharging case, you'd connect around like this, and you'd get that 0 equals the direction of the voltage across the capacitor, and then the current would be going in the opposite direction for the resistor, so it would be minus I times R. Or doing the same trick we did here, it would just be 1 over C times Q minus R times dq dt. Now, this discharging circuit, this looks a little bit more tractable to me. It looks to me like that's something I can solve. So let's look at that equation. I would have 1 over C times Q equals R times dq dt, or Q equals RC times dq dt. Okay, and so to me this looks like something I can do something with. All right, I noticed I made a little error here. When we're discharging, the direction of the current going through here will actually be negative. So the direction of the current is opposite the direction of the charge on the capacitor. So since we've got that extra minus sign, this is a plus on this, and it becomes a minus over here. So this should be a minus RC. And what you find then is that the solution to that equation is Q equals whatever you started with, so this is whatever charge you started with, times e to the minus t over RC. Okay, so I encourage you to go ahead, do the derivative, stick this back in, and you'll see that this in fact is the correct solution. Now let's just go over this in a new way. Okay, so here is our our rule. Kirchhoff's rule for the RC circuit charging is that we have our charge is increasing, and it's getting up to the point where we just have Q equals C times V. So that's our C times the battery voltage. Now to get that to work, we have to use a form that includes our C times E, and if we put in T equals 0, this would just be 1, and our Q would be 0. But if we put in T equals really big, this term goes to 0, and then we just get Q equals C times V. Okay, so how do we know that this works? Well, go ahead and you can take the derivative of this, and you would get this form. And then you can just plug in your Q and your dQ dt into this equation and confirm that it works. So the same thing is true with your discharging solution. You'll remember that we had our case before, but then we had a minus on here, so this turns it into essentially the same equation, just with a 0 on that side. And this one I think is a little bit easier to see how it works, is that the charge is eventually going to end up being 0, but it starts out, if you put Z equals 0, at whatever charge is initially on your capacitor. So that's going to depend on just your C times V. So I know this is a little bit of a confusing subject for students when they first come upon it. So I want to just do a couple of quick homework problems, and I have X homework problems because I didn't actually assign them this time, and I don't intend to put much RC circuit stuff on the test. All I want to put on there is maybe one multiple choice question about charging versus discharging. So in this problem it says an uncharged 5 microfarad capacitor and resistor are connected in series to a 12-volt battery and an open switch to form a simple RC circuit. So there's your battery. Here's your resistor and capacitor. So you have a resistor and you have a capacitor. And that's your RC circuit. And at the beginning it's uncharged. You have a break in the circuit, and then at time t equals 0, you take that switch and you go burp, you close it. It says to us the time constant of the circuit is 4 seconds. So what does that mean? That means that R times C equals 4 seconds. Part A of this question is, what must the resistance of the resistor be? Well, to get the resistance of the resistor, you know the time constant, so it must just be C divided by T. So in this case, our C is known. We have 5 microfarad capacitors, so whoops. Sorry, I screwed up there. R is T over C. Okay, so T over C, so that would be 4 seconds divided by 5 microfarads, so that would be 5 times 10 to the minus 6 farads. Seconds divided by farads equals ohms, so there you get your 8 times 10 to the 8th ohms. Now part B asks, what is the charge on either plate of the capacitor after one time constant has elapsed? Well, after a million time constants elapse, you would expect there to be 5 times 12, or 60 microcoulombs. So farads times volts is coulombs. So eventually you will get up to, you start, here's your time, here's your Q, you're eventually going to get up to your C times V. But after just one time constant, it asks us what is the charge. So let's just use the formula here. Q equals C times V. So that would be our 6 microfarads times E is 12 volts here. That's the voltage of the battery. And then we would just take 1 minus E. And then here, RC is our time constant. So our T we're said to be 1T over RC. So that's also T. So this is just e to the minus 1. Okay, and you can plug that in your calculator. This will give you some fraction, and you'll find out that it's around 38 microcoulombs. Okay, so it's pretty straightforward once you know what you're talking about. Let's take a look at another one of these problems. This one is sort of an interesting one because the discharging of a RC circuit is an example of exponential decay. And that's the same sort of thing that you come across if you're thinking about the decay of radioactive elements, for instance. And let's see what it says. In physics lab, Rebecca measured the voltage across an unknown capacitor in an RC circuit. Every 10 seconds after the switch in the circuit that allows the capacitor to discharge is closed. The capacitor was initially fully charged. Using the graph, estimate the time constant. Okay, so you want to find R times C. So you want to find that. Well, let's think about how you do it. If I have, I'll show you the most traditional way to solve this problem. The most traditional way is to figure out what your half-life of this. So that's the time it would take for the voltage to drop in to. Now, the thing to realize is that the voltage is proportional to the Q because Q equals C times V. So if you want to look at the Q over Q naught, Q over Q naught would be the same as C over C, CV over CV naught. Okay, so the C cancels out. So when you're comparing currents, comparing charges, it's going to be the same essentially as comparing voltages across a capacitor. So if we look here are voltages around maybe 6.4 volts. If we want to look, where do we get half of that? So around 3.2 volts, something like that. It looks to me like that's happening about like this. So this is 10 seconds. This looks about 15 seconds. It looks like the time it took for me to go from to 1/2 of the amount of current that I had was 5 seconds. Okay, so this should be tau. So what I can do there is say, how much time did it take me to go from from my Q naught to 1/2 Q naught, okay, those cancel out, equals e to the minus 5 seconds over t. So that now is an equation that I can just use my math to solve. So I have 1/2 equals e to the minus 5 seconds over t. Now, depending on what you did in pre-calc or in high school, this may look either like, oh, I have the tools to solve that, or oh no, this is bad. The way that you solve this is by doing a logarithm of both sides. So if you take ln of 1/2 equals ln natural log of e to the minus 5 seconds over tau, what natural logs do is it takes stuff out of the exponent. And so I can go ahead and take my log of 1/2 equals minus 5 seconds over tau. And then I can just go ahead and find that my tau equals minus 5 seconds over ln of 1/2. And without going too far into this, this is the same as saying that this is 5 seconds over the log of 2. Okay, so if you go ahead and solve that, you're going to find that the time is about 7.2 seconds. So that's your RC. So I probably won't have you solve this type of problem on your exam, but I do want you to have seen it because we are going to be returning to these time-dependent circuits in the future. Okay, so just to recap, what are the really important things that you should take away from this unit? Well, I have things that you want to know by heart and things that you want to be able to access after thinking. Things that you should know by heart is about the capacitors holding charge. You should know Q equals CV. The amount of charge on the capacitor is dependent on its capacitance and its voltage. You should know that current is the amount of charge passing by a point through a surface per unit time. So amps is coulombs over seconds. So that should be in your bones. You should know that V equals IR, that Ohm's law. So these are the things that you really are going to have to memorize and really be on your toes. Things that I expect you to be able to use your equation sheet and do is to think about energy storage in capacitors, power loss in resistors. So that would be this and this. So I'll give you those formulas. Remember, I've posted the formula sheet already. And also to be able to think about parallel and series circuits for resistors and capacitors, be able to do a little bit of Kirchhoffs laws, and be able to do just think a little bit about charging and discharging on RC circuits. Okay, so that's all of Unit 2. It's not a tiny amount of material, but I hope it is masterable. So on Monday we will come back, we'll do a review, and then next week we will take our test. All right, so good luck, and I will see you again soon.